Greetings. In this one I will show how to diagonalize a matrix with this example. So it's a 2 by 2 matrix, and in order to diagonalize a matrix, what it basically means is if this matrix that I'm looking at is A, then it can also be written as P, D, P inverse, where P and D we don't know, and the goal here is to find them out. And this can be written also as A, P equals PD because of multiplying on the right hand of both of the sides by P. But that's not significant. Actually, we might use this equation to check afterwards our result, if it actually goes. But so this is basically the point here. The matrix A should be equal to PD times P inverse, and PD we don't know. So we're trying to look for that. And exactly the needs for that are to know the eigenvalue and eigenvectors of this matrix. That's it. So as long as one is able to do that, there's just very short steps to just get to the result and actually directly obtain P and D. So first of all, to get eigenvalues, one gets eigenvalues the way that one takes the matrix 1, 4, 3, 5 in this case, and on the main diagonal you subtract lambda times the identity one. Basically, subtract lambda once on the main diagonal from all terms on the main diagonal. And then take a determinant of this one. So the determinant of this one and equal it to 0 and find the result for lambda. So that is the point. So 1 minus lambda, 5 minus lambda, this is taking the determinant, by the way. These are all prior knowledge, how to solve the quadratic equation or to take determinant. I expect that to be known before proceeding to such a context. So how to solve this? Well, 5 minus lambda minus 5 lambda plus lambda squared minus 12 equals 0. Lambda squared minus 6 lambda minus 7 equals 0, factorable as such. And then that yields to result lambda equals minus 1 and also equals 7. So these two results for lambda. So lambda is the eigenvalue. Lambda is the eigenvalue. So I can call two lambdas because we have two eigenvalues. The first one was minus 1, the second one was 7. Now, we need to find eigenvectors. So only using these two values, we already know how to create D. And for P, we need eigenvectors. So eigenvectors are obtained using eigenvalues. Before, we had this matrix. So we took A, that's it. And we subtracted lambda on the main diagonal always. And now we know lambda. So there's going to be two cases, when lambda is 1, minus 1, and when it's 7. So what is this going to be for the case of minus 1? Lambda is minus 1, then it's going to be 2, 4, 3, 6. Now, I want to solve this matrix for equaling to 0, and then the result will be my eigenvector. So, solve it to equal to 0. Well, this row by row reduction is the equivalent to this first one. It's 1.5 times bigger, so I can ignore it. And I can only use this one. But because we have two variables for one row, one equation, if I even shortcut it more, it ends up being this. Because we have two variables in one equation, one of them will have to become a parameter. We don't solve for both. And I will make x the parameter. So y is minus 1/2 x. And the result should be in the form xy. That should be the vector 1, the eigenvector number 1, the eigenvector for lambda 1. Well, that should be x and y. Well, what are x and y? We know y is minus 1/2 x. So it's actually in terms of x. And the x itself is x. So actually we have the parameter x inside it. So that's it, what we need. So basically because we had to have the parameter x, then at the entry of x it's x itself, and then at y it's y in terms of x. And then I extract the x out to get constants inside the vector. And the constants are what's unique about it. Then this just means you can multiply it back and forth many ways. All the span of it, but this is the unique direction of the vector itself. So the actual eigenvector is this 1 minus 1/2. So eigenvector number 1, we just got it. Eigenvector number 1, I'm calling V1 is 1 minus 1 half. And then we need eigenvector 2, and after that we'll be actually able to know both P and D from here. I'll show you how to directly translate it to PD. So basically now we do the same thing, but we do it for lambda equals 7. So take this matrix with the subtracted lambda on the main diagonal, lambda equals 7, well, that creates minus 6, 4, 3, and minus 2. And again, find the kernel for it. Alright, no, find the null space, find the result to this matrix equaling 0. I create this augmented matrix for it. But again, this is a piece of knowledge to be known before proceeding to this kind of topic usually. So again, the second row actually ends up being equivalent to the first row in meaning. By row operation I can disregard it, and then row number 1 says this, and that can be simplified to minus 3 plus minus 3x plus 2y equaling 0. Again, I will express y in terms of x, so y will have 3 halves x. And x itself is, again, so v2 will be again x and y, but x again is the parameter that we don't know x. There is just one equation and two unknowns. So x is, I say x, and for y I express it in x, so that's 3 halves x. But again, I can take out the x. So instead of, so these were our calculations here now. Instead of this, I will take the x out, replace it by 1, right? And that's it. But this is just a scaling factor. So for the eigenvector, I'm just saying this. This is the unique thing about it. So 1 and 3 halves. These are our two eigenvectors and these are our two eigenvalues. And now, how to construct P and D? D is called the diagonal matrix because the way we will construct it is it will be only filled for diagonal entries, and the diagonal entries are going to be precisely the eigenvalues of this matrix. So D for A contains its A's eigenvalues, so minus 1 and 7. So that's going to be D. And then P is going to be the two eigenvectors. For eigenvalue 1, which is on this one, that's the minus 1, we have eigenvector 1. So in that column should be 1 and minus 1 half, and in the second one, the remaining one. So 1 and 3 halves. And this is the result. So these two turn out to fulfill the properties behind it make it work. You can check for yourself, explore more. We might actually go into it in other videos to explain more deeper the context of everything. But this is the process. And okay, so for the end, we might want to multiply it and see if it works. So we can actually do that. So AP should equal to PD. And you see P and P on both sides, but A and D are different. And just because of the change of the order of the multiplication, we need different matrices to multiply P on either side. That means that actually there's not the commutativity in matrix multiplication in general. For some matrices, it will end up being the same on both directions, but for some not. So, and usually not. So let's do AP equals PD. Actually, I should, so basically to check P and D are right, I could put it in this equation, but for that I would need to think of P inverse. But instead, I will do AP equals PD as a, let's say, a quicker way. So, I'm checking this because these two are equivalent. A times P. P is 1, 1 minus 1 half and 3 halves. And it should equal to 1, 1 minus 1 half and 3 halves times the diagonal, which is minus 1, 7. How we multiply matrices, I will not go that deep into. It's row times column dot product. Which row by which column, that's already to know how to multiply matrices. I'm not going to go into it very closely in this one because, again, that's a thing that is usually taken into account before such a topic. So, I'm just going to say that on both sides the result will be a 2 by 2 matrix again. Just one. And on both sides. And it should equal, of course, because we have the equal sign and we're expecting it by this equation. That's what we're checking. And you might see the pattern or you might not, if in case you don't know how to multiply matrices, but I'm going to just do it here. This one is going to be left matrix row, first row, times right matrix first column. So 1 minus 2. Then this one is going to be 1 times 1 plus 12 times over 2. So it's 7. This one is going to be 3 minus 5 over 2, which is 1 over 2. And this one is going to be 3 plus 15 over 2. Or actually it's going to be 1, 4, 3, 5. Yes, it's going to be 3 plus 15 over 2. But it's 6 over 2 plus 15 over 2, so it's 21 over 2. Alright, and then we have this one, so minus 1 plus 1, plus 0. Then second one is 0 plus 7. This one is 1 half plus 0. So actually it ends up being the same. And then 0 plus 21 over 2. So yes, it is satisfied, it works. So we have verified it. The P and B were found correctly, and yes, we did obtain a P and D that fulfill this equation.